A very good evening to all of you. Am I audible to all of you?
Yes, ma'am, you are audible.
Okay. Okay, thank you. A very good evening to all of you. I extend my warmest welcome to each and everyone present here on the second day of 1 week online course on stochastic processes, theory and its applications in medical sciences, sponsored by Ministry of Human Resource Development MHRD under the scheme of Global Initiative of Academics Networks GYAN. Thanks to all of you who joined us this evening. This is going to be another evening full of knowledge, full of experiences, queries, and suggestions. Before we carry on with the expert sessions, we would give our regards and appreciation to Professor Rajiv Kumar, coordinator, and Dr. Poonam Redhu, deputy coordinator of this course, who have made this course a reality. Now, without any further delay, let me introduce the first speaker of the day, Dr. Poonam Redhu. She is presently working as assistant professor in the Department of Mathematics at Maharishi Dayananda University, Rohtak. She obtained her doctorate degree from Indian Institute of Technology, IIT Ropar, Punjab. She has published many research papers in reputed journals and currently she is working on mathematical modeling and traffic flow. She has presented papers in international and national conferences in India and abroad. She has also been awarded by financial support from ICIAM 2015 Beijing, China, where she delivered the extension lecture in the webinar. She has also acted as the referee of many journals, including Physics Letter A, Physica A, and Non-Linear Dynamics, etc. Welcome to Dr. Poonam Redhu. Now it's over to you, ma'am.
Thank you, Dr. Meenakshi, for a nice introduction. Yes, good evening to all of you. Firstly, I would like to thank MHRD for sanctioning this GYAN course to our department and also our head of the department, Professor Rajiv Kumar, for organizing this event. So without any delay, I will start my lecture. Yes. Is my screen is visible to all?
Yes, ma'am, it's visible.
Okay. So the title of my lecture is Mathematical Modeling and its Application to the Diversified Field. So the content of my talk like that. Okay. Firstly, we study about mathematical modeling, then why we need the mathematical modeling. After that, we study some classification of mathematical modeling, then its basic application with its sensitivity analysis. So let's start with very basic, what is a model? So a model for any system or you can say any process is a representation of real object or situation. so that we can know that how this system will work on the basis of present work. The model can be classified into four types. First one is physical model, semantic model, a verbal model, and mathematical model. So let's start with the physical model. So it is clear from its name also that represent a physical construct whose characteristics resemble the physical characteristics of the model system. Like if we are planning to make a house, then what is the design of that? For that we make a okay, I don't we make a design for that, a smaller copy of that. And also if you want to make flyover or you can say bridge anywhere, then we also need a abstract form of that in smaller copy. So these are the physical models. Then semantic model. So it is a representation of element of a system using abstract, mainly graphics we used to model the realistic pictures. So like in organizational, you see that there is a hierarchy from lower to higher. So in earlier time, we use the maps from going from one place to another place, but again, it will become very easy with the help of GPS. As you see in many factory industry, there is some order. So firstly, we get raw material, then that will be supplied to the supplier. After that, the manufacturing will be done and that is sent to the distributor. Then after distributor, it will send to the retailer and then we get this information. So in also hospital, you can see that firstly you goes to the fee receipt and then go to the doctor. Also there is some intermediate order between that. So everywhere you are using this semantic model. In institute, in any organization, in industry, factory, everywhere we are using this model. Next one is verbal model. So verbal model, like if you are planning to construct a firm or you are starting a business. So for that, we do the verbal conversation with our colleague or you can say with our partner that, okay, what location we need, how much money we need to start that business and how many manpower we need. So all these things can be done in the form of verbally. So there we use the verbal model. Next one is a mathematical model, which is the base of all the models you can say. So mathematical model is a representation of real world problem and situation of physical system in the form of simplified assumption. And this assumption can be in the form of mainly in the form of equations. So this equation help us to understand the fundamental of original problem. Once you understand the problem of a fundamental system, then you can apply it for future predictions. So like in weather forecasting, we are using mathematical model. In blood flow, you can say in water flow and how our heart is working. So everywhere there is mathematical modeling. So before studying the mathematical model, there is a process. Okay. Okay, just a second. So what is scientific process? Okay, initially we have a physical system. Then from that system, we observe and collect the data. And after collecting the data, we make some concept. We make some concept about that. And basis on the concept, we apply some physical law like Newton's law. So after that, we develop a mathematical models. Okay, once our model is developed, then it is correct or not. Okay, what are the assumption we made again? So for that, we solve this mathematical model by using some method, mainly numerical methods. So after getting the result, we interpret this result with the like with the, with the or real system data. So, or you can say experimental data. We have already experimental data, then we compare this data with the results. So, if these results are matching with the experimental data, then we can say, okay, our model, we are success, that our model is okay, and we use this mathematical model for future prediction also. But if this data is not matching, this result are not matching with the experimental data, then what we have to do, we again do this process, like we observe the data, then concept, after going like this. So in this way we can correct, or you can say update our mathematical models. So this is the scientific process of the mathematical modeling, any kind of mathematical modeling. Now, we already studied what are the basics. So what is the importance of mathematical modeling? So it play an important role in the analysis of system which other model can't do. Like physical model, chemical, linguistic model can't do that. And it is the best way to understand the physical system. Everything we can't understand, but it can be easily interpretable with the help of mathematical mode. And it also helps us to discover new feature about the problem. So like say experimentally we can't do everything. So once we have a mathematical model, on that model we can apply new features which we can't do experimentally. And it is capable of saving life, assisting in policy decision making. You everywhere see that. The inverse, it helps understand the universe and the condition needed to the sustain to the life. So there is mainly two type of classification we already studied yesterday. But apart from this, there are also many like statics, non-static, study, non-study, discrete, non-discrete. But we are not going in detail of that. So as you know, in the physical system, we have an important physical problem, that is the traffic flow problem. So before going to study the traffic flow, we have some basic knowledge about traffic flow. So what is traffic flow? So it is a study of interaction between vehicles, driver and infrastructure, so that we can minimize the traffic congestion and maximize the traffic flow on the road. So every day in our life, we face the problem of traffic congestion while going from one place to another place. Somewhere I am saying that congestion is when jam there. So in the, let's say one of the best example of this traffic congestion, or you can say jam, is that was in 2010 on the, it happened in 2010 on the Beijing Tibet highway in China. It was 100-kilometer long and lasted for 12 days. So such type of problem, physical problem, help motivate us to work in the field of traffic flow modeling. Now, what is the aim of our traffic flow modeling? So main motivation behind traffic flow like that, where to install traffic light or stop signs we install. Then after installing traffic light, what should be their timing? Okay, then where to construct flyover or not, so that we can reduce the traffic congestion. In which place we construct flyover or not. So at the obviously when there is congestion or say jam, then at that area, at that place, we construct the flyover. And how many lanes to be built on a new lane highway? Okay, and then where to make construct entrance and exit. And it also has many application in computer science, engineering and mathematics. So our general aim of this mathematical modeling is like maximize the traffic flow. Okay, and then eliminate accident, minimize automobile exhaust pollution, even also reduce the noise pollution, increase safety on the road, and our main and last is the avoid traffic jam, so that we can move from one place to another place smoothly. So these are the main motivation behind traffic flow modeling. Now, to model any kind of physical system, there are mainly three levels. First one is the microscopic. In microscopic model, we focus on the individual vehicle, or you can say in general term, I can say individual entities, and trace information about it. For example, car following model, study of particle flow, cellular beta model. So initially, let's say I have two, three cars on the road. Then for each vehicle, for each car, I study the velocity, what is the headway there, let's say time t, the vehicle is at this position, then how many times it will, how much time it will take from one place to another place. That is a microscopic model. Next one is the macroscopic model. So in this model, we don't focus on the individual vehicle. So in this model, we study the property of system at aggregate level. So, if you look the traffic at the night time from a higher place, you can see that you are not able to see the vehicle. It look like as a particle is moving inside a tube. Okay, so that is a macroscopic model. Like conservation of mass, hydrodynamic model. These all are the example of macroscopic model. Third one is a mesoscopic, which is the intermediate stage of microscopic and macroscopic. So, like, for example, gas kinematic model and cluster model. So, what we do here we make the cluster, and each cluster there is a number of vehicle. Okay, and then for each vehicle we study the about the like velocity, space, headway, and all these detail that come under the category of mesoscopic model. So there are mainly three type of, you can say three fundamental variable to model the traffic flow. First one is a flow. Okay. So it is a number of vehicle passing through a point per unit time, and it is denoted by usually Q, which is n x comma t plus delta t is the number of vehicle between the time period t comma t plus delta t at point x, and delta t is the time, is the time instant. So n is a number of vehicle here. Next one is velocity. So all of you know what is velocity. That is rate of change of displacement with respect to time t. But here we take the averages of that. Okay, let's say I have n number of vehicle on the road and each of a velocity vi. Then we take the average of that. That is v. Next one is a density. The local density is the number of vehicle per unit distance at time t, or it is usually denoted by rho. So what is the relationship between them? That is rho xt is equal to q, which is a function of xt upon vxt. Or you can say q is equal to rho into v. V is a function of here rho. Why? Because let's say if the number of vehicle on the road is high, then obviously velocity will be low. And if the number of vehicle is low, then velocity will be maximum, or you can say higher. So here we depend upon rho. As you can see from this graph, that is left hand side, given by this is between velocity and density. As you see the blue curve, so for the along x-axis, you can see that when the density is low, velocity is maximum. Okay, but what happened here? When the density is high, then velocity is low, and in between that is monotonically decreasing. So this is the velocity diagram for the velocity and density. Now, in right hand side, you can see that there is a graph between q versus rho. Q is the air flow and rho is the density. So you can see that initially here, as density increases, the flow is increases. Okay, up to some level. Let's say here rho c is known as a critical density. Critical density, why? Because here velocity start to decrease. So the graph is also decreases. When the density is high, then our flow will also decrease, because here you can see Q is equal to rho V. So if density is high, obviously velocity will also decrease. So this reason up to a rho C, that is known as free flow, and after that, that is congestion flow. Okay. Also in congestion flow, there is you can say there is a situation of jam, but also a jam of many kinds. Jams and every vehicle stop. Okay, that is a maximum density. But somewhere you say that there is jam, but vehicles are moving with their smaller speed. Okay, that also come under the category of congestion flow. So these are the fundamental variables. Okay, now let's start with the microscopic traffic flow model. This is a journal case. I have two cars on the road. As you can see on the left hand side, two cars are moving on the road. Car one, the velocity of car one is not constant, but V2 is constant for second car. So as time passes, because car 2 is moving with constant velocity, the car 1 after some time t reaches a catch to the car 2. So what is the logic behind that? That is, the speed of car 2 is higher as compared to this. Also, there is one more thing, that is, the car 2 have also maintained the distance with the car 2. So what are the basic variable here? Like what is velocity? Velocity also matter here. Then space, number of vehicle भी यहाँ पे also matter, number of vehicles and how many number of lanes, and is there overtaking or passing. So all these are factor related to the this flow, car following. So what is the model equation here? So that is, so here you can see that is dv jt over dt. Here j represent the car number. Okay, and a, that is equal to a capital V, that is a function of delta xj, that is a space headway minus vjt. Here a is the sensitivity, which is equal to 1 over tau. What is tau here? That is a reaction time. Means after sensing the information, how much time driver will take to react. Okay, he will accelerate how many, after how much time, and v is here optimal speed. Okay, usually we will take that is a optimal a minus local speed. So vj cannot be greater than v. So x is the space coordinate obviously here. So this is the differential equation for one vehicle. Okay, in real life we have so many vehicles. Okay, so in this way we have a system of orderly differential equation. If we want to compare this result with the experimental data, then we will solve this problem with the help of numerical method. Mainly the method used are finite difference method, because this is simply a basic equation. So you can use finite difference method, forward finite difference method. Okay. Next one is the macroscopic traffic flow model. Okay. So here I will teach a basic model, that is a lattice hydrodynamic model, that come under the category of this macroscopic. So let us this is the road which is given by here, colored is yellow. This is a road and we discretize the road. Okay, that is also in our language we say this is other lattices. So on this road, for a simple model, we consider a same type of vehicle, like all the cars, uniform vehicle, or one kind of vehicle you can say, and there is no entrance or there is no source and sink. Sorry, it is written wrong. There is no source and sink. Source means there is no attached road that can enter in this main road. Also not sink there. That from this road vehicle can go outside. Means there is no link road in your language. So the number of vehicle entering this region, the same as of number out. outgoing from this region. So means the number of vehicle in this region remain conserved. Conserved means you know that the conservation of mass, that is a continuity equation, that is a basic of fluid dynamics. Okay, so here to model this equation we have a continuity equation. So that is given by first equation, curl T rho plus rho naught curl X rho V. Rho is the density here, V is the velocity. Okay, rho naught is the average density. Obviously, A is the sensitivity of the driver. And also, how the flow is changing. For that, we have a Navier-Stokes equation. So here we give it name as the flow evolution equation. What is that? Curl T rho V is equal to A into rho naught V rho X plus delta. Okay, delta is the distance minus rho V. This is a local flow and this is the optimal flow. Okay, so again, what is capital V here? Well, capital V's are here equilibrium speed. But again, how we choose this function? Actually, there is so many function studied in the literature for capital V, that is equilibrium velocity. So from experimental data, researcher come to the conclude that V is equal to V max upon 2 tangent hyperbolic 1 by rho minus 1 by rho c. Here rho c is the critical density I already told in the graph plus tangent hyperbolic 1 over rho c. So this is the main shape of the optimal velocity function, equilibrium velocity function. Okay, so this is our model equation. Now what is the latest version of this? So latest version of this is curl T rho j plus rho naught rho j vj minus rho j minus 1 vj minus 1. Simply here we discretize the space, but here time is the continuous. So this is a semi-discrete model. And again we do same for the flow evolution equation. So here if I am taking V is the equilibrium velocity function and V is the function of rho. So as you see in the velocity versus density graph, that if the density is low, obviously velocity is high, and if the density is high, then velocity is low. So V, curl V over curl rho are monotonically decreasing function. And when rho is 0, obviously Q क्या है हमारे पास यहाँ पे? Q is flow, that is equal to 0. And when rho is equal to rho max, means Q is equal to 0. Rho is equal to 0 means there is no vehicle on the road. No vehicle on the road means there is no flow. And when there is maximum density means there is m, that means there is velocity is 0. So the product Q is equal to rho v, but here v is, if v is 0 then Q is equal to 0. Okay. For any type of mathematical modeling, we do the sensitivity analysis. Okay, we study a mathematical model by using two analysis, theoretically or simulation, through simulation. So here we do the linear analysis. Before doing to the linear analysis, we give the uniform condition to our model. So here it is rho naught and visa function, that is a function of rho t. So let perturb the density with some perturbation function. Let's say rho jt is equal to rho naught plus yjt. Here rho naught is a uniform density and yjt is a small perturbation. So after putting this value in our main equation, we got this equation. As you can see that our perturbation we give like that, there is a maximum change with respect to time t. So that's why we choose the perturbation in term of exponential function. Here a is the amplitude, exponents I, k, j for the lattice and z for the, z is a new variable. Okay, we will study, I will told this about again. T is the time. So what is z here? Z is equal to again in term of iota k. So after putting this result, we got this stability condition. This is the graph between tau A versus headway. Or if you take 1 over head width means that is a density. What is the relationship between density and head width? That is 1 over head width. Okay, because here everything is in averages. So as you can see, the curve, this is called the neutral stability curve, which divide our region into two type. First one is stable region and unstable region. Stable means there is no jam. Every vehicle is moving their optimal speed. Means free flow है हमारे पास. And the reason below this curve, that is a unstable region, means there is a jam situation. So this is the basic model of macroscopic traffic movement. But in real life, as you see, there are many complicated factors which affect our traffic. Like let's say passing. Okay. So if um, at the j plus 1th position there is a car, okay, and let's say it is at j point. So the driver look, there is some space inside this and he try to overtake or overpass. So in that case, we have this factor, but we have to add this term, okay, where it will affect our model. Okay, but again, there is no entrance or exit, or you can say there is no source and sink. But so the equation of continuity remain same. But in flow evolution equation,
I have a question here.
yes,
So, while examining the macroscopic behavior,
yes,
how do we develop such mathematically rigorous equations? Because these equations are so very mathematically rigorous.
okay. Actually, these are the basic. Did you studied about conservation of mass?
Yes, I studied conservation of Mars probably in the sixth or the seventh class.
Okay, okay. So it like that. The
I mean, which equation refers to the conservation of the mass?
okay. Let's forget about the traffic. Okay, I have a tube. Okay, so some liquid is going from the left side and something is exiting from the right side. Okay,
Yes,
so initially we have initial position and final position.
right.
Okay, and how this mass is changing with respect to time t, that is given by the component curl t rho g. Okay, rate of change of mass, okay, within the tube, or you can say
Right.
on the road. This is equal to T
Mhm.
is equal to minus time of this flow, flow at the right hand side and minus flow at the left hand side. But if you take the, as I'm saying that the same amount of liquid is entering and same amount of liquid is outgoing. So what will be inside?
So the volume, I mean, we measure the volume of the liquid, which was depending upon the length of the tube. We compute the volume of the fluid inside.
But if let's say there is no source sourcing, the
No
same
source
amount
of.
will enter, same amount obviously out.
No, it is true that the amount which enters within the tube would be same as the amount exited from the tube. That is true.
Yes.
But then probably, I mean, but how? I mean, all the mathematical models may not be that much simple, and moreover, the meaning of, I mean, this equation is uh, not well understood actually.
Okay, you can
And what could be the meaning of the stability analysis? Sensitivity analysis makes some sense.
okay.
Perturbation makes some sense, but what could be the? I mean, how did we write that equation for the stability analysis?
Okay, actually, that you are talking about that stability analysis that we usually do in our models. Stability means if we give the perturbation to the system, how it will behave. Okay, this
Mhm,
perturbation will increase with time or it will
mhm.
decrease. So, what is the effect of this small perturbation on our system, on uniform flow? it will decrease with time or it increase. So that analysis is known as a stability analysis.
Okay.
Okay, sensitivity for the particular parameter here. But here stability, that overall, if we are perturbing some system and then we are observing that what is happening there. So that is a stability analysis. Okay, there is difference.
Okay.
Also, in stability, it can be linear or no linear. Linear means you are just perturbing the system with a small perturbation. But in no linear, you can see the perturbation will be very big. So it is so much big, once you perturb, the things cannot become to the its original state. Okay, that command, that study will be the stability analysis.
Okay.
Yes.
All right.
And you are talking about this conservation. This is the main basic of the mathematical modeling. Conservation. You also know heard about the continuity equation?
Continuity
I think
equation.
you didn't. Yeah, you didn't heard. One more thing I want to tell here, that in traffic, you see that the vehicle move unidirectionally, but in fluid flow, the particle move in backward as well, forward as well as forward बैकवर्ड दोनों साइड में मूव कर सकते हैं फ्लूइड फ्लो के केस में. क्यों? क्योंकि उनके बीच में एक इंटरमोलिकुलर फोर्स भी होता है और वो एक दूसरे को आगे पीछे पुश करते हैं. बट ट्रैफिक के केस में ये फिनोमिना नहीं होता हमारे पास. ओके, तो वी आर एट द पॉइंट दैट पासिंग. ओके, so up to here, okay, just a second. Can I stop the presentation? I want to share another mode.
Sure, ma'am.
Okay, my screen is visible to all?
Yes, visible.
Yes. Okay. So this is the continuity equation. Firstly, this is a continuity equation, and up to here you study that this is the flow evolution equation, or you from fluid it is Navier-Stokes equation. So due to the passing, a new term is added here. Okay, in term of optimal flow. So local flow means rho j into Vj, but here it is optimal flow. Rho into rho naught is here the average density and V is the optimal speed. Okay, so here we what we will do. So let's say I am at the jth position. Okay, at jth position here. I look at the forward that obviously I can see two sides or more than two sides, depend upon the driver. Okay, I see the flow here and here, but my position, what is the position y? That is J. So I look at this two position and I take the decision that okay, my speed will be depend upon this difference, that is at J plus 2th minus at J plus 1th. So all these are in term of flow. Okay, so what is the main yes? Please share. Okay. Thank you. So here, what will be the effect on and on which equation? So this is important here. So obviously, due to the passing, the effect will be goes to the flow evolution equation. So here we added this term. Here you can see that is rho naught v rho j plus 1 at time t minus rho naught v rho j plus t. Obviously, this term we are taking like that. Thus, everything will be in dimension. Left hand side and right hand side will be in dimension. Okay. So in physics also you can see if we are adding some term here, then it will be the dimension will be same on both the sides. So this here gamma. What is gamma here? That is the passing rate. Okay, at which rate they are passing. So normally we take the value of gamma between 0 to 1. Okay, that is the effect of passing. Now in our general life you see that, let's say you are driving, you sense the information at time t. Okay, and after how much time you take the decision? Okay, there is a many factor, like you take the decision. Firstly, let's say you sense the information at time t, then take your decision after some time. Let's say that is t plus tau 1 plus tau 2. What is tau 1 here? That is a delay response in sensing headway, कि आपके सामने स्पेस है या नहीं, आप उसको आप आपके दिमाग तक उस इंफॉर्मेशन को लेके जा रहे हो. ओके, दैट रिस्पॉन्स इज tau 1. और क्या है, आपने once you have the information, then maybe due to the car, because that is a machine, so it will also take the time to the response, like in accelerating. So the many researcher, or you can say in our daily life, we see this effect, that is the driver anticipation effect. If we are able to consider this effect in mathematics, then it becomes very easy for engineering and also other, that what is the behavior of traffic by using driver behavior. Also, one more thing is very interesting. By using driver anticipation effect, as you see the self robot car, selfless driver car, so all these are they are using this model. Okay, so that is a driver anticipation effect. What is alpha? Here I am taking the remaining term remains same, but here I introduce a new term. Okay, so earlier it was at v rho j plus t. So obviously we are doing everything in follow evolution equation. Depend upon our problem, that is t plus alpha tau. What is alpha here? Okay, that is a driver anticipation effect. If alpha is positive, means t plus अल्फा टाउ या अल्फा लेट्स में मैं यहाँ पे हम ले लेते हैं 0.8 समथिंग. ओके, टाउ. So alpha greater than 0 means driver is more active, so he take its decision in advance. Okay, he see that he or she see that on the road that like मेरे आगे इतना जैम है, या मैं यहाँ से मूव करूँ या पासिंग करूँ या मैं लेन चेंज करूँ, वो एडवांस में ये जो इंफॉर्मेशन है वो पहले ही ले लेता है. ओके, बट इफ अल्फा इज नेगेटिव, ओके, सो अल्फा इज नेगेटिव मीन्स देयर इज डिले. ऑब्वियसली जो हमारे पास ड्राइवर है वो क्या कर रहा है, डिले कर रहा है इंफॉर्मेशन को सेंस करने में. सो दैट इज द नेगेटिव anticipation effect. Again we do the analysis for that what is the effect of this alpha on our results. Okay, so this is a phase diagram space in parameter space rho and a. This is the sensitivity, and here which is denoted by a, and this is the rho here. As you see here, this is for a particular value of gamma. Gamma is 0.06. That is if there is a passing. Okay, here you can see the black curve. Okay, the solid line is the neutral stability, come from the linear stability analysis, and the dotted curve come from the, that is known as the that come from the non-linear analysis. Okay, and the reason between them the coexisting phase. So as you see that if I increase the value of alpha, the region above the solid line is stable region and below that is unstable. Stable means there is a free flow. Okay, and below that unstable means there is a Z. So as I consider the effect of alpha, you can see that the stable region, that is free flow region, is increasing. Okay, so that is also happening in our real life. If driver is more active, that there is less jam. Okay, next is an important effect, that is a interruption. Let's say there is some interruption on the road, then what will happen there? So it will be more clear from this. So P here P is the probability that at which rate the interruption happen on the road. So again, here P is a probability. You can also consider this model under stochastic model. Okay, stochastic process. That is a stochastic model. So here you can see that for P is equal to 0, that is given by that is represented by the red line. If I increase the, as we consider the effect of P, as you can see that the stable region is increasing. This is the effect of interruption. As you also see from this plot of density difference that our stable region is increasing. These are the very difficult. I think
What
all
is
of
P
us
here?
it is very difficult.
Ma'am?
Yes.
Ma'am, what is P here? And I'm not understanding the conclusion of the graph.
P is the interruption probability. Okay. So as you see there, so here Pj plus 2 at the, let's say there is some interruption at the j plus 1th position. Okay, and due to this interruption, obviously the flow will be affected, and this will be considered like that. So here Pj plus 2, I'm saying that this is the interruption probability. So there is interruption means here gamma 1 represent the reactive coefficient of interruption. Okay, then यदि हमारे पास यहाँ पे interruption है, that will come with some probability. Okay, that is here you can see.
Ma'am, what is the criteria of multiplying this probability with these terms? I mean, being beginners, that it is difficult to understand these mathematical terms which are added or subtracted in these terms.
Okay. So as I told, let's say here at j plus 2th position, okay, there is a interruption. So let's say I'm at the position G. Up to now, this is the flow evolution equation. Okay. So if there is a interruption, then obviously to go at the next position, I will stay at the j plus 1th position. So that why, so if you are looking for the, if you want to move forward, यदि आप लेट से मैं कहती हूँ कि आप jth पोजीशन पे हो, ठीक है, आपको j प्लस 1th तक जाना है या j प्लस 2 तक ऐसे जाना है, तो ऐसा तो नहीं है कि आप अकेला इस चीज को कंसीडर करते हो. आपने जस्ट एक आपने जस्ट आपको स्पीड वाला बटन आपने प्रेस किया और जस्ट आप यहाँ पे पहुंच गए, बट वो भी तो देखोगे ना यहाँ पे आपके पास स्पेस है नहीं है, हाउ मेनी नंबर ऑफ व्हीकल्स देयर, तो आप इन दोनों का डिफरेंस लोगे. यहाँ पे व्हीकल्स कितने, ऐसा तो नहीं कि जस्ट मैंने यहाँ पे तो देखा नहीं है, यहाँ पे j प्लस 2h पे नहीं देखा मैंने, जस्ट यहाँ पे देखा, तो भी इसलिए है जो फ्लो हमारा, हम फ्लो कैसे करेंगे, j प्लस 2h पे माइनस j प्लस 1h पे, हमारे नंबर ऑफ व्हीकल कितने हैं या स्पेस है नहीं है, वो चीजें हम कंसिडर करेंगे यहाँ पे. तो उसी के लिए और लेट से मैं कहती हूँ कि j प्लस 2h पे हमारे पास क्या है, इंटरप्शन है, ठीक है, तो यदि मैं jth पोजीशन पे हूँ तो ऑब्वियसली मैं यहाँ तक आऊंगी j प्लस 1 तक, यहाँ तक तो नहीं जाएंगे, यानी ये चीज मेरे को इफेक्ट ही नहीं कर रही, तो इसलिए यहाँ पे जो j प्लस 1 है वो वाली टर्म मेरे पास नहीं है. सो वो मेरे पास है ये जो गामा 1 फैक्टर है. आप जैसे कह रहे हो कि ये मल्टीप्लाई हम कैसे करते हैं, ऑब्वियसली यदि हम कहते हैं कि something is proportional, rate of change is proportional to something, then obviously for proportional there is some constant. Okay, that's why this constant are coming here, and I'm saying this is coming with some probability, so that's why probability multiplied here. This is flow. Okay, what is q there, rho into v. See, this is q, this is rho, this is v, and again everything is in the term of flow.
Okay.
Yes. So this all about the passing driver anticipation. Let's say there is some interruption on the road, but as you see there is also the effect of road structure. Road structure means there is gradient highway. So in general, I'm not going to the model. I'm just explaining here. So as you see that obviously I'm saying I'm taking basic model. There is no sink and source. Okay, so our continuity equation remain here. Continuity equation remain same. Again the effect is going on the flow evolution equation. Okay, up to here I think you know everything. दिस इज अ फ्लो इवोल्यूशन इक्वेशन कंप्लीट ये भी है बट हमने यहाँ पे क्या किया ऑप्टिमल करंट डिफरेंस लिया कि ज्यादा से ज्यादा हमारा फ्लो इतना हो सकता है हमारी फॉलोइंग व्हीकल का ठीक है तो हेयर वी टुक द इफेक्ट ऑफ थीटा अब थीटा जो हमारे पास है मैं कहती हूँ वी इज अ फंक्शन ऑफ जीरो ओके अर्लियर बट अगेन इफ दिस इज अ ग्रेडियंट हाईवे ओके सो मेरे पास मान लो लाइक दिस मेरे पास ग्रेडियंट हाईवे है तो ओबियसली इट विल इफेक्ट अवर डेंसिटी डेंसिटी मीन्स अगेन explicitly I can say it will affect our velocity. Okay, so here theta is the inclination angle. Let's say I have this smooth road and this is the our uphill. So with x-axis, this is the angle, that is the angle of inclination. And similarly, this is the uphill situation. Okay, and similarly for the downhill situation, this is a theta angle. This is downhill. So as you see on the roads, that if the road is more inclined, your velocity will be less and there is less number of vehicle on that. Okay, so like मैं कहूँगी it is inclined with the angle 0, it is inclined with angle 2 degree, 6 degree and 8 degree. Okay, so if there is more inclination means there your velocity also reduced and the number of vehicle on that region is also reduced. Okay, so means there is free flow. In generally we can say free flow. And similarly, in case of downhill, what will happen?
Dr. Poonam,
Yes.
ma'am, we are running short of time. If you can conclude within 5 minutes, please.
Oh, okay, ma'am.
Thank you.
So this was a case of gradient highway. Again, as you can see, most of the road are made up of 2 or more lanes. Okay, so this is the situation. Let's say I have 2 lane, lane 1 and lane 2. If I'm discretizing the road. Okay, so let's say at this position in lane 1, the number of vehicle is more as compared to this. So obviously we try to change our lane. So vehicle goes on this lane and obviously the density at this point or at this point is high, then obviously the vehicle goes to the lane 1 from lane 2 to lane 1. This is a concept of lane changing. Okay, so this is all about the 2-lane highway. Okay, next one is you can see circle on the road network. Okay, so this is a road map structure of Chandigarh city. Okay, these all are the sectors. Okay, and these are the roads. So to model this type of problem, we extend our model for 2D, two-dimensional network. So these all are the lattices. This is the x-axis, this is the y-axis. Here C is the fraction of vehicle are moving in x direction and 1 minus C, the remaining vehicles are moving in y direction. So what will happen? Okay, so again the continuity equation remains same. Okay, and the same flow evolution. And what is the new term here? That is a new equation for x-axis and a new dynamic equation. Dynamics, or you can say in along x-axis or also y-axis. x-axis के along भी और y-axis के along भी हमारे पास क्या होगी continuity equation भी होगी and also flow equation. But total density क्या होगी? Let's say मैं ये कहती हूँ यहाँ पे total density क्या होगी हमारे पास? मैं let's say इस point की बात करती हूँ. Okay, so इसके corresponding मेरे पास this is row, okay, let's say row I empty, और इसके corresponding मेरे पास ये है row I x और plus row j y, इन दोनों का सम हमारे पास total density होगा इसके. Okay, so as you see, if there is equal number of vehicles move in both d directions, c is equal to 0.5. Okay, means 50% vehicle are moving in x direction and 50% vehicle are moving in y direction. So there is a smooth kind of things. So the our graph like this. Okay, but if again I'm saying that 20% vehicle are moving in x direction and remaining are moving in y direction, so obviously there will be jam in the y direction. Okay, so that is the concept of two-dimensional network. Okay, so this is all about from my side. Any question? So if we are trying to model any kind of physical system, okay, firstly, if you have an experimental data, it is very good. Okay, if not, then you have to collect. Okay, if you are not able to that, then basically make mathematical model from that. Firstly, what is important here? What are the factors involved in that modeling? Okay, then basis on that, you make a model. Okay, so if you have not experimental data, then try to relate the things, real things, okay, real results or real concept with this model. Okay, in first time you can't make a best model, but if you are also everything you can't add in one model, because if everything you are adding in one model, it will be very complex and it is very hard to solve. So every time I'm saying this term is added, because everything we can't do in one model, like two-lane highway on two dimensions. Same in population growth model. As you can see that we have simple model population growth. You can't add everything like birth rate, how many of birth rate, death rate, immigration, everything you can't do in one model. Okay. So basic is to understand the concept factor which are influencing our physical system. So this is all about from my side.
Thank you, Dr. Poonam. Dear participants, now there will be break of 5 minutes. After that, we will be starting our next session.
Good, Poonam. Nice to
Thank
hear
you,
the
sir.
sessions.
Thank you, sir.